Today, we are going to deconstruct something we do thousands of times a day without even thinking about it, taking a single step. We're going to pull back the curtain and see just how a simple thought becomes a physical reality.
I mean, really think about it. You decide to move your leg, and it just happens. But that's the result of an unbelievably fast and complex chain of events. So how does a fleeting thought in your brain actually tell your bones and muscles to get a move on? Well, let's find out.
To get to the bottom of it, we're going to go on a little three-part journey. First, we'll trace that initial spark, the signal from your brain. Then, we're going to zoom way in to the microscopic engine of muscle contraction itself. And finally, we'll see how all that force actually moves your skeleton. And believe it or not, our story starts not in your leg, but up in your head.
Right, so part one. It all begins in the command center, your brain. Every single conscious move you make, no matter how tiny, starts right here as just the spark of an idea.
Every voluntary action, and I mean everything from blinking your eyes to sprinting for a bus, it all kicks off with an electrical signal from your central nervous system. This signal zips down a specialized nerve cell called a motor neuron, which acts kind of like a super fast data cable connecting your brain to your body.
And this is where we get to a really critical handoff point. The nerve doesn't actually touch the muscle. Nope. It stops just shy of it, at this tiny gap called the neuromuscular junction. When that electrical signal gets there, it triggers the release of a chemical messenger, a neurotransmitter called acetylcholine. This chemical floods that little gap and tells the muscle fiber, "All right, it's go time."
Okay, so the order has been delivered. Now we turn to the engines that are going to execute that command, your muscles. These are the absolute powerhouses that turn that chemical signal into raw physical force.
And get this, they are a huge part of who you are. For the average adult, muscles make up a staggering 40 to 50% of your total body weight. That is nearly half of you, just an incredible amount of biological machinery that's dedicated purely to getting you moving.
Now, not all muscles are created equal. You've got cardiac muscle just for your heart and visceral or smooth muscle for your internal organs like your stomach. You don't control those consciously, thank goodness. But for our story, for taking that step, we are focused 100% on skeletal muscles. Those are the ones attached to your bones, the ones you have voluntary control over. So, the big question, how does a skeletal muscle actually contract? To understand that, we have to zoom in. I mean way in, down to the molecular level, to look at this absolutely beautiful mechanism called the sliding filament theory. This right here, this is the sarcomere. See those repeating patterns of light and dark bands? Each one of those little sections is a sarcomere. It's the basic functional unit of a muscle. Think of them like millions of tiny little engines all linked together in a long chain. And when they all fire at once, that's a muscle contraction.
The main players inside that sarcomere are two proteins, actin and myosin. The easiest way to think about them is that actin is like a thin rope, and myosin is a thicker rope that has all these tiny club-like heads sticking out of it. The entire magic of muscle contraction is basically these myosin heads grabbing onto the actin rope and pulling. That's it.
And this pulling action happens in a super rapid 4-step cycle. First, that signal from the nerve causes a flood of calcium ions. They act like a key, unlocking binding sites on the actin rope. As soon as those sites are open, the myosin heads latch on. Then you get the power stroke. The myosin heads pivot and pull that actin filament inward. And finally, a little molecule of ATP, our body's energy currency, comes in and makes the myosin head let go, reset, and get ready to do it all over again.
And this is the brilliant result when that cycle repeats thousands of times a second. The thin actin filaments get pulled inward, sliding over the thick myosin ones. You can see the whole sarcomere just gets shorter. Now imagine millions of these shortening all at once, and boom, the entire muscle contracts, generating force.
So we've got this signal, and we've got the force from the muscle contracting. But force alone isn't movement. For that, you need a solid framework for the muscle to pull on. So now, let's bring in the skeletal system and see how this force actually becomes movement.
The adult human skeleton is just a masterpiece of engineering, made of 206 individual bones. This incredible framework gives us structure, it gives us protection, and crucially, it provides the rigid levers that our muscles need to pull against to make us move.
The skeleton is basically divided into two parts. First up, you have the axial skeleton. That's your skull, your spine, and your ribcage. Its number one job is protection. Your skull, for example, is just this hard, bony vault that protects our most important organ, the brain. And in the same way, the rib cage acts like a bony shield for your heart and lungs. That whole protective core is the axial skeleton. But for movement, for taking that step, we need the appendicular skeleton. That's your arms, your legs, and all the bits that attach them to your core. This is the framework that muscles are actually going to put into motion.
And this is where it all finally comes together. The relationship between your muscles, bones, and joints works exactly like a simple lever. The muscles contract and generate the force. The bones act as the stiff lever arm. And the joints are the pivot point, the fulcrum, that allows that force to create this huge range of motion.
You know, this whole system is really a symphony of perfect coordination, with countless parts all working together in perfect harmony. But that complexity also means there are a lot of places where things can go wrong, which can lead to a whole variety of movement disorders.
And this is why understanding the biology is so crucial. It helps us understand what's happening in these disorders. Myasthenia gravis messes with that neuromuscular junction, that critical signal handoff point. Muscular dystrophy is a degeneration of the muscle fibers themselves, and conditions like arthritis and osteoporosis attack the joints and bones, the very levers and fulcrums we need to move.
So the next time you get up and walk across the room, just take a second to appreciate the sheer, mind-boggling complexity behind that one simple act. It's a perfectly timed symphony of electrical signals, chemical reactions, sliding proteins, and mechanical levers. An ancient, elegant system all firing in perfect harmony. So the only question left is, what will you do with your next step?